Hi guys, so this is my discussion for redox reaction and I'll be giving some examples at the end of this discussion. So when we say redox reaction, it's a type of chemical reaction in which the oxidation states of atoms are changed. So um, we have discussed the oxidation states before and I hope you have remembered the table that I gave you on the oxidation states and how we combine different chemicals to arrive at a specific chemical combination. So these reactions are important in many areas of chemistry, including biochem and electrochemistry. So since we are discussing analytical chemistry, we'll be delving more on the importance of redox reaction on electrochemistry. So more discussion on electrochemistry will be on our next and future videos. Okay, so some other redox reactions definition includes oxidation, reduction, the process of losing electron in a chemical reaction, and reduction is the process of gaining electrons in a chemical reaction. So let's say first I'm gonna give you a mnemonics for this topic. So for my mnemonics, it is Leora and also Geroa. So if you have other mnemonics that works best on this type of discussion, you can use it. But for me, this one's the best mnemonics that I've been using for over a year already. So when we say Leora, it means losing electron. That will be oxidation, and uh, it happens. And the one that is being oxidized is also the reducing agent. Well, when we say Jeroa, it means gaining electron. The process is called reduction. And the one that is being reduced is your oxidizing agent. Oxidizing agent. Okay. So another example, I'm going to give you another example to further elaborate this mnemonics that I've been giving you. So for example, we have zinc on its metallic form plus copper sulfate, and then we're going to have a zinc sulfate and then copper. So first off, before we delve to this discussion, you have to understand and know about oxidation states. So every atom has different oxidation states. So let me share my periodic table to you. Say for example, we have zinc, right? We use zinc. So if we're going to check the oxidation state of zinc, we have different types. So we have uh, hold on. Okay, for zinc, it's just two for a while. Let's have iron. So for example, iron, we have plus one, plus two, plus three, plus four, plus five, and plus six. So that's why I have told you a while ago that before you go into a discussion of redox reaction, I do advise that for you to know first on how to look for a specific oxidation number of different type of compounds before delving or dwelling into oxidation or redox reaction. So like this one, if you see an iron on a specific reaction, say for example in ferrocyanide, no, FeCN, you have to understand if it's ferrous, if it's gonna be ferrous or ferric. So you have to have a computation for that, and it's another topic. So we're gonna focus more on redox reaction for now. So for zinc, we only have plus 2 as an oxidation state, so we have no problem on that. But hold on. If you are going to see a zinc such as this one with no oxidation state, that means it is a stable form of zinc, which is most likely metal. and the oxidation state for that is usually 0. If you haven't seen any +1 or +2 on the upper right hand corner of each element, that means the oxidation state of that element is equivalent to 0. Okay, and for copper sulfate, since copper have a lot of oxidation state, let us check copper. Again, copper have +1 and +2. So +1 is the cuprous and +2 is the cupric. So it can also be seen as Cu +2 and Cu +1. So for that, we have to know if the copper here is +1 or +2. So that's when our discussion of oxidation state will come, okay, or will be involved. So we have copper sulfate. For that, we have to create an equation wherein copper will be your X plus sulfate is a compound that is polyatomic. So if you're going to look for the oxidation state of sulfate, the oxidation state for that is +6. Oh, sorry. The oxidation state for that is -2. So if this one is -2, sorry. Okay, so if this one is -2 and the overall charge for this one, as you see, we don't see any +1 or +2 on the upper right hand corner in this area. So that means the overall charge for copper sulfate here is 0. So in this case, if the charge of the sulfate is -2 and the overall charge is 0, we will come up with an X value of +2. So that means our copper here is your cupric or your +2. Okay, so that's how to find your oxidation numbers in a specific polyatomic compound. So more discussion and example of that will be on our next video or on our future video. So next one is your zinc sulfate. No, so for zinc sulfate, zinc here is again unknown, but the zinc here uh, will have, if you're going to find again the oxidation state of your zinc, that will be X plus -2, since -2 is the oxidation state of the polyatomic compound sulfate, and equivalent to an overall charge of 0. Again, why 0? Because you haven't seen any upper right hand corner number or oxidation state to the overall compound. So usually they are denoted as with a parenthesis such as this ones, or we'll see 0 on that. But for in this case, no, on this case, we don't see any of that. So that means the overall charge of this polyatomic compound is 0. So in that case, X is equivalent to +2. So that means the zinc on this area or on this part has a +2 charge. And as you may see, copper here doesn't contain any oxidation state. That means this copper here is metal and is stable. That means the charge of this copper is 0. So if you are going to check for the movement of electrons on each of this element, we'll see that your zinc here from 0 become +2. So again, from 0 it becomes plus 2. So that means um, there is a electron decrease. You may be confused because it is gaining with a +2, right? But I'm saying that there is a losing of electron in here because the charge of electron is negative. Remember that. And on this area, from 0 to +2 means losing more negativity. That means this one is decreasing the oxidation state. Um, we'll have more discussion of that on copper. But as you may see, instead of becoming more negative, instead of becoming more negative, your 0 become more positive. That means there is an electron decrease. So this will be your losing of electron, losing of electron. So that means this reaction is called oxidation. And your zinc here is your reducing agent. If you're going to ask which is being reduced, that the element that is being reduced by your reducing agent is your copper, because your zinc is your reducing agent. Okay, so next one is, I'm gonna change the color. Okay, the next one is your copper. So from positive 2, your copper becomes 0. From positive 2, your copper becomes 0. So that means from positive 2, it became 0. So that is gaining an electron, because from positive 2, it became nearer to the negative value of your copper. So it is decrease rather than in it increase in negativity, because it is nearer to the negative value. 0 is nearer to the negative value, so there is a decrease or of positivity or gaining of electron. Now that it is gaining more electron, the process is called reduction. And copper here is your oxidizing agent. Oxidizing agent. Okay, so what is being oxidized? So copper here is oxidizing your zinc. Okay, so that's the relationship between oxidation and reduction. Okay, so I guess we touched on all the topics, all the definition in this slide. So oxidation is the process of losing electron in chemical reaction. So remember the remember the Leora mnemonics that we have on that. And reduction is the process of gaining electron. Remember the Geroa mnemonics that we have on that. So oxidizing agent is a substance that causes oxidation, and by taking electrons from from another substance. And reducing agent is a substance that causes reduction by donating electron to another substance. So let's see on our reducing agent. Our reducing agent is your copper, and according to the definition, a substance that causes reduction. So this caused the reduction of zinc from 0 to positive 2, and by donating electron to another substance. So your copper donates electron. Um, your zinc donates electron from another substance to copper. That's why it became positive 2, because it loses electron. And same for our oxidizing agent. Okay. So this is a brief introduction on the history of the oxidation number concept. Okay, let's skip to that. And okay, so again, for this one, we'll be dwelling more on oxidation reduction on electrochemistry. Okay, and on electrochemistry, we will be discussing more of um, activity series and priority rules, since it is talking about the movement of electrons and the reactivity. So the activity series is a list of metals in order of their reactivity. So uh, this determines which element will combine or have a reaction to another element in the equation. So actually, activity series has been discussed on your, I think, inorganic chemistry as an introduction. And priority rules are used to determine which metal will be oxidized and which will be reduced in the redox reaction. So this activity series and priority rules is actually helpful to know the whole structure of your chemical equation. So we also have your electrochemical cell. This is again an advanced topic for your electrochemistry. And electrochemical cells is a device that converts chemical energy into electrical energy. So a classic example for this is your battery. Inside the battery, there is a redox reaction that is happening. So that is why there is a movement of electron. So which is the movement of electron is actually the definition of your electricity happen because there's a movement of electron. And we also have your relative activity of metal in an electrochemical cell is determined by its position in the electromotive force series. Okay, so these are some of the industrial application histories. Let's skip to that too. If you are interested on this, you may pause and have some research on the following. Okay, so again, this is the history of the redox reaction in organic chemistry and how they are being used. Okay, so redox reactions are the basis of galvanic cells and standard electrode potential. So this is a more principle of the electrochemistry discussion. So let's do balancing equation. Let's do balancing equation in acid and base environment. Okay, so acid and base are very important components of chemical equations, and understanding how to balance them is essential for a successful experiment. So acid and base reactions is a very important chemical equation in acid and base. When we are balancing equation, knowing if it's acid or base, or saying knowing if the um, environment where the reaction will take place is very important. Say for example, I have a beaker in here with a hydrochloric acid inside, and then I added the the chemicals that we have discussed a while ago. I added zinc, and I also added copper sulfate. Say, for example, I both added this on the beaker with hydrochloric acid. So that means the environment where this reaction will take place will be in an acidic environment. And for that, you have to consider when balancing an equation the acidic environment that it is in, because the balancing of that depends on the balancing of electrons available in this chemical reaction will depend on its environment. So before, we only know how to balance. We learn how to balance the specific element, the number of element. But for now, we're not just going to balance the specific number of element, but also the electron present on both sides of the equation. So we'll discuss that depending on the environment that we have. So the types of acid that we have is a strong acid, we have the weak acid, and we have the organic acid. You have to understand and remember that strong acid dissociate completely, and while weak acids does not, or partially dissociate. So same for our bases. Okay, so we have strong bases, weak bases, and we also have your neutral bases. Okay, so equilibrium in acid and base reaction is important concept when balancing chemical equation. So I think the most important principle that we learn on the equilibrium is the Le Chatelier principle, but we'll not discuss on that on this topic. But if you wanted to search principle. Okay, so this is the Le Chatelier principle, which is very important in equilibrium since it defines how the stress is being relieved in a certain equation and what will happen on a certain equation in a certain environment. So, say for example, this is a beaker, and Le Chatelier principle says that in a specific, say for example, sodium plus chloride will become sodium chloride, no, in a pH 7, and Le Chatelier principle explains that sodium chloride doesn't remain just sodium chloride. The double-sided arrow means it is reversible, meaning in an equilibrium it is continuously shifting in this certain environment. So when we add something, say for example, when we add another sodium, there will be a lot of concentration of sodium chloride in the equation. So, for enable for it to balance the equation, we have to shift the stress to the left, or to the react to our product side. So, more discussion of Le Chatelier principle will be on another topic. So we also have your acid and base, Lewis acid and base. So Lewis acid and base is an important component of balancing equation. Lewis acids are, it defines that Lewis acids are electron pair acceptors, while Lewis base is an electron pair donor. So you may be asked in the exam or in your quizzes or in your assessment, which in this following equation of redox reaction is your Lewis base or Lewis acid. So you have to take note of this one. Okay, so we also have the definition, and we also have discussed, I think, the conjugate acid and bases before when we are discussing about the Lewis acid and base. So to balance the equation in acid and base reaction, you have to identify the acid and base in the reaction first, and then calculate the number of the oxidation number, and then we have to balance the equation. But aside from that, we not just balance the number of element, but we also balance the number of electron on both sides of the equation. So let's have an example for that. Okay, I'll just skip this one. Oh, these are some household items. Common acid and base. So vinegar is an acid. It's acetic acid. We have baking soda, real lemon juice, and we have your ammonia. Okay, so in an acid and base reaction, the most common type is the acid and salt reaction. So this is the most common acid and base reaction. Okay. So one example of our that we are going to discuss is, I sorry, I'm gonna copy it on this sheet so it'll be easier to discuss. We have permanganate, that's negative 1, plus sulfite, negative 2. Hold on. Okay, so in balancing acidic solution, the first thing that you have to do is compute for the oxidation state of all atoms that is found in this equation. So for our manganate, permanganate, that is Mn. Sorry, let's use blue to differentiate. MnO4. Okay, so as we have discussed before in our oxidation state, to compute for the value of your manganese, since we know that oxygen is always negative 2. Oxygen is always negative 2 unless it is combined with hydrogen in the case of hydrogen peroxide only. But for this case, no, oxygen is always negative 2. So do not confuse it with the negative sign out here as the sign for your oxygen, because this negative signage is the overall charge of your potassium permanganate. So let's not confuse it for the charge of oxygen. For your manganese, we'll use X to denote its presence, plus your oxygen that has a negative 2 oxidation state times 4 from the atomic number is equivalent to negative, which is the overall charge, which is negative 1. So let's label it. X again is your manganese. 2 is the oxidation state. Of oxygen, and then 4 is the number of your oxygen atom present. Okay, and your negative 1 is your overall permanganate, MnO4 charge. Okay, so if you wanted to screenshot this message, you may do, but I'm gonna erase it for now to make sure that everything is clear. But the answer for this equation is x plus negative 8 is equivalent to negative 1. So if we're going to move negative 8 on the other side of the equation, we'll have positive 8. And the answer for manganese oxidation state is positive 7. So if we're going to cross-check it to our manganese value of oxidation states, so we have positive 7. So that validates our computation of our oxidation states for manganese. So our manganese, I'm going to delete it, this one. Our manganese value is positive 7. Okay. This may look a bit long, but when you are already accustomed on computing for oxidation state, it will be much easier. So this one is positive 2. Our oxygen is negative 2. How about in our sulfur trioxide? Okay, we're going to compute for the value of sulfur since we know that oxygen is already negative 2. So for that case, sulfur will be your x plus negative 2 times 3 is equivalent to the overall charge, which is negative 2. That will be x plus negative 6 is equivalent to negative 2. Then we move negative 6 on the other side of the equation. That will make it positive 6. So the answer for this one, sorry. Okay, the answer for this one is x is equivalent to positive 4. If you're going to look at the periodic table for the sulfur value, we'll see that there is a value for positive 4, making our computation valid. So we have x is positive 4. And again, we know that oxygen is negative 2. So I'm going to delete it again. Okay. Okay, next one we have your manganese. For this one, for this one, positive 2 will be our oxidation state. Why positive 2? Because this is just a monatomic, meaning there is only one atom in here with your positive 2 oxidation state. For our sulfate, SO4, negative 2, we have to compute for our sulfur since we know that oxygen is already negative 2. So your sulfur will be your X plus negative 2 times 4 is equivalent to negative 2. So if you're going to compute for that, plus negative 8 is equivalent to negative 2. Moving negative 8 on the other side of the equation, making it more positive, the answer for our sulfur oxidation state will be your positive 6. If we are going to validate the oxidation state of our sulfur, positive 6 is also available. So that will validate our computation that it is correct. So your sulfur here will be positive 6 and our oxygen again is negative 2. So we don't have to look for it anymore. So, why do we have to go through this very hard computation for each of the elements? So we'll know which one is our oxidation and which one is our reduction, which one is the reducing agent and which one is our oxidizing agent. So let's see, from our manganese 7, going to change the color. For our manganese, we have positive 7, it became positive 2. So in this drastic change, we have go down 5 step below. So our positive 7 will have positive 2. That means we are decreasing the negativity. We are decreasing the positivity and making it more negative. So what happened here is gaining of electron. Why we gain electrons? Say for example, look for this one. Positive 7 plus 5 electron, which has a negative value. This is like saying negative 5 and then we arrive at positive 2. That is why I was saying that you gain 5 electron. Okay, in this case. So let's remove that. So what happened here in our manganese is gain of electron. And gaining of electron is your GEROA. If you're going to remember our mnemonics. So that means it gain electron. And what happened here is reduction. So our manganese here is our oxidizing agent of the element sulfur, because sulfur is being oxidized. So we'll know if it is really sulfur. So let's see. Sulfur out here, let's use different color. Okay, so our sulfur here is from positive 4, it became positive 6. So what happened here is it gained more positivity. So that means it is losing negativity, right? So it is losing electron because it became more positive. So that means losing electron in our mnemonic is your Leora, which is losing electron. What happened here is your oxidation, And your sulfur is the reducing agent of the element manganese. So, sulfur here reduce manganese. That is why the event that happened on manganese is called reduction. And your manganese here oxidize your sulfur. That is why the event that happened on sulfur is called oxidation. Okay, so now that we know this data, okay, let's move on. Now that we know this data, we can do half cell reaction. So what happened in half cell reaction? Let me rewrite our problem. So our problem is MnO4 minus plus SO3 negative 2 became manganese plus 2 plus sulfate negative 2. So again, let's write the oxidation state. This one is positive 7. This one is negative 4 or positive 4. This one is positive 2. And this one is your positive, sorry, this one is 6. Positive 6. This one is positive 4. Okay, now we write a half cell reaction. So what do you mean by half cell reaction? Half cell reaction is when we first perform the balancing of equation on the first element, on the first process. Say for example in manganese, the first process of reduction. So we write half cell for manganese, which is MnO4 minus, it became Mn plus 2. So what happened here is we have to balance this manganese. And as you may see, manganese, they both have one number of manganese, but on the reactant side, we have an oxygen. So to balance it out, we have to add, remember that for every oxygen, we have to balance it out on the other side with water. For every hydrogen, we have to balance it out on the other side with your hydrogen also. So let's perform it. So we have to add on the other half side with H2O or water. Okay, so if you can see, the oxygen in this side is 4. So we have to add 4 as a coefficient of your hydrogen to compensate for the oxygen on the other side. Now, if you're going to list the number of oxygen and hydrogen on both sides, manganese is 1, oxygen is 4, we have 0 hydrogen. Here we have 1 manganese. This one is an oxidation state. Do not be confused. It is not the number of atoms. So oxygen here is 4 and our hydrogen here is 8. So as I was saying, on the other side, we don't have any hydrogen. To balance it out, we have to add hydrogen. We have to add 8 hydrogen. Okay? Once you have balanced each element, we have to balance the number of electron present. So if we're going to check, hydrogen always have positive 1 electron. Okay, and hydrogen here has 8. We have 8 atoms of hydrogen. That means we have positive 8 because we have to multiply this to 8. And we have positive 8 plus, how many electron is this? So we are not going to look for each, just like the ones we have done here in identifying which one is oxidizing, reduction, reducing agent, and oxidation. We are not going to go through each of them. That is just for identifying which one is oxidation, which one is reduction. So for this one, balancing your electron, we just have to look for the overall oxidation state. So for this one, our permanganate has negative 1 overall oxidation state. On the other side of the equation, we have positive 2 plus, since this is a polyatomic compound with no charges, this means water is stable and therefore the charge of it is 0. Okay, so always remember that This one has positive, always have positive one. Always remember that if you haven't seen any charges on the upper right corner of each element, it is stable or it has zero as its overall oxidation state. So for this one, positive 8 plus negative 1 is positive 7. And we have to equalize it with the other side. So this one is positive 2. So remember, to um, to make it balance, to make the electron balance, we have to add electron. So the difference of positive 7 and positive 2 is 5. So we have to add 5 electrons. So if you're going to ask which side would you add 5 electron, of course we would add that to the highest number. So for this one, we have 5 electron. So remember that if we are going to add 5 electron here, say for example, you were checking if you can add 5 electron on the other side, you'll see that you'll arrive at negative 3 negative 3 electron as the charge of electron on the right side. Why? Because positive 2 5 electrons is similar to saying you have to subtract 3 electron to your positive 2. So sorry, you have to subtract 5, sorry, you have to subtract 5, and for that you'll gain negative 3 as an end result. So that is not a bit nearer to our positive 7, which is our goal to balance out the electron in both equations. So we add 5 electron on the other side. Okay, so why do we add 5 electron? It's similar to the equation negative 5 plus positive 7. So the ending result of this one would of course be positive 2. So positive 2, we have now an equal equation of positive 2. Okay, so what we added is 5 electron, and that 5 electron will go on your reactant side or your left side of the equation. So let me add that 5 electron. Now that we balance out the electron and the equation on both sides, we're going to go on the next or the second half cell, which is sulfate, sulfur trioxide and sulfate. So on this one, the only unbalanced one is your oxygen. That will mean we have to add one water on the other side. And for the product side, we have to add 2 hydrogen. So let's see if it's already balanced. Sulfur here is 1, oxygen here is 3 plus 1, 4, hydrogen here is 2. Your sulfur here is 1, your oxygen here is 4, and your hydrogen here is 2. So I think that balance out our equation. Now that we already have balanced number of atoms, sorry, balanced number of atoms on both sides, we have to balance again the electrons. So for water, as I have said before, it doesn't have any charges on uh, the right side or the overall charge. That means the side for our water is 0. And for sulfur trioxide, it is negative 2. So on the other side, we have negative 2 plus, we have negative 2 plus 2. So that will mean this one is negative 2 and this one is 0. So the difference between negative 2 and 0 is 2. So instead of adding 2 on your left side, we must add plus 2 electron. Again, this is similar on saying 0 plus negative 2 since the charge of electron is negative. So that will mean negative 2 is equivalent to negative 2. So where did we add the electron? We add it on the right side. So plus 2 electron. Okay, so now that we are finished on the half cells, we have to combine both of the half cell. So we have to write first the one from the left side, and then later we'll have to add the one on the right side. So let's add 5 electron. That will mean 5 electron plus 8 hydrogen plus 1 plus manganate permanganate negative plus this one H2O plus SO3 or sulfur trioxide. And then the other half of the equations, we have first manganese positive 2 plus 4 H2O. Make sure you are not leaving anything um, leaving anything out. Plus, sorry, I have to go to the second part. Plus SO4 negative 2 plus 2 hydrogen plus 2 electron. Sorry, it's a bit cramped, but um, now that you add each of them, we have to check for the number of hydrogen on both sides, and we have to cancel out everything that we can cancel on both sides. So I think I forgot I think I forgot another step. Okay. So before we write, sorry, I'm just gonna insert it here. We have to balance out the electron, of course. 5 electron here, and we also have 2 electron on the other side of the equation. We have to make it the same. So no, we have to rewrite everything. Okay, so for that, let's have the common factor for 5 and 2. That will be 10, right? So for to make 5 electron 10, let's use different color. To make 5 electron 10, we have to multiply everything by 2. And to make 2 electron 10, we have to multiply everything by 5. So in writing that, let's do first the manganese part. That will be 2 times 5e is 10 electron plus 2 times 8 is 16 hydrogen plus 1. It's a lot. And we have 2 permanganate negative charge, and we also have your 2 manganese plus 8 water. And for the other side, we have to multiply everything by 5. That will be 5 H2O plus 5 SO3 and then 5 SO4 negative 2 plus 10 hydrogen plus 10 electron. Okay, so this is the total equation. Now the only thing that we are left with is to add all of the following in one single equation. So for this part, I'm still gonna use different color. Okay, so we have 10 electron plus 16 hydrogen plus 2 permanganate plus this one. We have 5 H2O plus 5 SO3. Okay, I'm gonna use the lower part so it will not be cramped like the ones we write a while ago. And then we have this one, 2 manganese plus 8 H2O plus 5 SO4. I'm now on the side. 5 SO4 plus 10 hydrogen plus 10 electron. Now that we have combined both of them, we have to cancel out everything that we can cancel to simplify the equation. So say for example, we can cancel 10 electron on both sides. Let's cancel that out. We can also cancel 6 hydrogen here because we have 10 hydrogen. So that will leave us with 6 hydrogen on this side. That will be 16 minus 10. So that sums up, the difference will be 6 hydrogen. And then we have water. You can cancel water. That will be, that will remain, we'll have remaining of 3 hydrogen. Okay, so I think that's everything that we can cancel. And then we'll rewrite the equation. So that's a very long one. So that will be 6 hydrogen plus 2 manganate per manganate plus 5 SO3, then 2 manganese plus 3 H2O plus 5 SO4 negative 2. So this is the simplified equation. So for the checking, let's see if it's correct. So we have manganese, we have oxygen, we have sulfur, we have hydrogen. Okay, so again, we have manganese, oxygen, sulfur, and hydrogen. So for the atom, manganese, we have 2. Oxygen, we have 5 times 3, 15, plus 2 times 8 times 4 is 8. So that will be, I think, 23, 15 plus 8. And then we have sulfur, we have 5 sulfur. And we have, how many hydrogen? We have 6 hydrogen. So for this side, we have 2 manganese. We have oxygen is 3 times 1 is 3. Then 5 times 4 is 20. That will be 23. We have sulfur, which is 5. And we have hydrogen, which is 3 times 2 is 6. Okay, so I think everything on our atoms is now balanced. How about our electrons? So let's see. On the other side, we have 6 electron plus we have negative 1. So that will be 2 times negative 1. That will be negative 2 plus 5 times negative 2. That will be negative 10. Okay, so the total of electron on this side is um, negative 2 plus negative 10. Okay, 6 plus 2, negative 2 is 4 plus negative 10, that will be negative 6. Let me know if it's correct. For this one is 2 times positive 2, that will be positive 4 plus this one is 0 since water is stable and it is inert and it has 0 charges. And then we have 5 times negative 2, that will be negative 10. So the total is negative 10 plus positive 4, that will be negative 6. So everything now is balanced. We have a balanced equation and a balanced atomic number and also a balanced um, electron. So that's how you balance our um, in acidic reaction. It's a bit long, but um, we're gonna use the same equation in balancing basic reaction. So it's actually the same step with your acidic reaction, but there's an additional step at the end, which is this one. So let's copy the equation again. Now we already have a balanced equation, which is 6. Sorry, we have 6H plus 2MnO4 plus 5SO3, 5SO3 or sulfur trioxide, and then we have 2 manganese plus 2 plus 3H2O plus 5SO4 negative 2. So if you're going to balance it, we notice first that we have an acidic environment because we have a lot of hydrogen in here. So the goal here is to convert that hydrogen into a hydroxide. And for that, we're going to start this equation by adding additional hydroxide for every number of hydrogen that we have. So in this side, we have 6 hydrogen. So we're going to add 6 hydroxide. which has a negative charge. That Now that we have 6 hydroxide on the left side, we must add. Let me see if I can squeeze it. Oh, sorry. Oh, okay. I don't know if. Okay, so since we add 6 hydroxide on the other side, we must also. Sorry, let's not copy it in. Let's add another hydroxide on the opposite side. So that will be 6 hydroxide here. Okay, now that we have that, we'll combine this one, and then it will become 6H2O. And then we have plus 2MnO4 minus plus 5SO3, and then it will become 2 manganese plus 2 plus 3H2O plus 5SO4 negative 2 plus 6 hydroxide. Now that we already combined these two, we have to cancel out what we can cancel again, like the ones we did before. So for this one, we have to cancel out water and the water on this side. So what will remain on this half side is 3H2O plus 2MnO4. Sorry for repeatedly writing it out. Plus 5 sulfur trioxide plus 2 manganese. Plus, we omit this one, so it will be 5SO4 negative 2 plus 6 hydroxide. So on this equation, we don't have any hydrogen anymore. We have 6 hydroxide, which make it basic. So that is how you balance equation in basic. So it's best to say that to balance equation in a basic environment, you have to do or balance first the equation in an acidic environment. So that's the whole computation for it. So for more example, you can check um, or you can try it out. Here are some of the examples. And you can pause this video so you can compute it, and the correct answer for this equation is this one. So I have another example for that. Again, you can pause this video and then return back for the correct answer. For this acidic solution, the correct answer for this one is this one. Okay, so I hope you understand redox reaction and how to balance equations on this video. Thank you so much.